Let's have a look at something that's called feedback control. So this follows on with the theory behind control theory. Control theory is something that is considered always in a robotics or mechatronics system, and these courses are usually quite advanced courses, quite mathematical courses, going into the whole analysis of how things are controlled, especially looking at it in an analog control system. And it's got its place. Yet I find that a lot of people start getting very scared about the topic of control systems, and they almost want to try and stay away from it. They don't want to attempt it. Yet when you look at what it actually consists of, it's actually a very easy principle to follow. So what I'm going to do is I'm going to go into the different types of control systems that are the common ones that are often used. I'll go through the math of it in terms of just so that you've got a very brief overview of how it is used. Then I'll go into the tuning of these control systems. And then once we've done that, then when I start looking at things in the programming side of it and in the coding of it, it will become then a bit clearer as to why these specific pieces of code are being used in. Okay, so the first type of controller is a proportional controller. So proportional control. You might also come across what's known as just the normal P controller, and that's just referring to proportional. Okay, the proportional controller has got a diagram that is as the following to represent it. So you've got some reference, you've got an adder over here, so it will add over there. It comes through to some plant, or what we'll have as a constant. This will be Kp, and then that will come out to an output U. And then we will have this feedback coming back to this adder being subtracted. Okay, so let's look at this in a way of application. So you're wanting to drive your vehicle, and most of the vehicles these days have got, especially the modern vehicles, have got a cruise control system in it. So you activate it and you can actually travel at a certain speed. You do not have to control this on your own, so you can essentially let go of the gas or the fuel pedal, and you can then actually then just focus on the road, and you don't need to concentrate on whether you're going too fast or too slow. And it's quite a nice feature to have. Okay, so let's say, for example, you're going and you're saying, well, I want to go at a speed of 60 kilometers per hour. Kilometers per hour. Okay, so that's your desired speed you want to go, and you set it at that. Okay, but keep in mind that motor vehicles, motors, engines, all these items are not always linear in terms of its output. You might be going up a hill, and suddenly you need to have more fuel going to the engine, so therefore you can't have a constant sort of voltage going out if it was an electric vehicle, or constant amount of fuel going to the engine. So you need to then increase the amount of fuel or the amount of voltage going to the engine. Okay, so let's say in this example you're going only at 40 km per hour. Okay, so that is the speed that the vehicle is now only going at. So essentially there's some error. Okay, so this 40 km per hour will come down. It will be added to this adder. So that will say, okay, well, it's 60 minus the 40 that's coming in here gives you a value of 20. Okay, So over here, you're going to then have a value of 20. Now that is known as your error. Okay, so we often refer to it as just an E. That's the output coming out of that adder. Okay, so that 20, now KP, we're just going to have that as a multiplier, and for this scenario, we're going to keep it as 1. So 20 multiplied by 1 is going to be 20. And that needs to then be added to the output over here of 40 kilometers per hour. And so therefore it will go and it will make it 60 kilometers per hour. Okay, so that's how the basic feedback loop works. It looks at what the difference is between your reference and your error, and it will add it to your output to correct it and to make it to equal to the reference. Okay, so now that you sort of see how that all works, if you have to look at control theory type of books, that will say your proportional controller, your P controller, has an output to be proportional to the error. So as we saw over here, the output then is proportional to the error. If the error is small, it will be only a small increase needed on the output. Okay, so in your common control theory textbooks would then have the equation for these proportional control feedback systems. U of t is equal to Kp, because there's that constant over there, multiplied by the E of t. So E of t is our error. Okay. And essentially, as we saw over here, that Kp in this scenario it was equal to 1, multiplied by that 20, which was our error, gives you 20. So that means that we need to say the output U is equal to what U was plus Kp multiplied by the error. Okay, so our output is equal to whatever the output was, and we add this error to it multiplied by Kp. So that's how this system would then, that's how we would be able to obtain 60 kilometers per hour over there, because if we took this 20 kilometers per hour over there multiplied by the constant of 1 for Kp in this scenario, that would be equal to 20 plus the 40 kilometers we had over there will give us then equal to 60 kilometers per hour. Okay, so that's proportional control. Now this equation that I've got over here, that's the one that's going to be probably the important one to focus on when we start looking at programming. Okay, so remember, error is equal to your output minus your reference value. Okay, let's have a look at integral control. Okay, that's also known as just I control. Okay, so the diagram for this looks very similar. You've got your reference, you're going through an adder, you're going to get an output which is your error. That's going to go into a Ki integral. I'm going to explain to you what that is now. Okay, that goes out to your output, and then this goes back and gets subtracted into your adder over here. Okay, so with integral control, it is the accumulative over time of all the errors until the set point is reached. Okay, so with integration, if you look at integration and you look at in terms of the definition of it, it is the sum of a certain equation. Okay, so your typical control books would give you the equation that for this integral control is U of t is equal to Ki, multiply that by the integral from 0 to t, e of tau d tau. Okay, and this implies that in a very similar fashion as we've done over there, u is equal to u plus ki times the sum of I is equal to 0 up to I is equal to the current value of error I. Okay, so essentially what you're going to be doing is you're going to be adding all the errors together as you're going along until you get to your set point value. And even at your set point value, your errors will be small. But keep in mind that these sum of errors is not absolute values of the errors. So sometimes your error could be negative, and then you need to add it and actually subtract the value, and eventually that value will decrease. Okay, so this is the sort of the approach that we will, the specific final equation. So one that we will be looking at. Okay, I is equal to 0 over there. I'm not scratching it out. Let me rewrite that over there. I is equal to 0. Okay, so that is the equation we will be looking at in a bit more detail when it comes to the programming side of things. Okay, and then finally you get your derivative control. And that's often also known as your D controller. Okay, so the diagram for your derivative control looks looks like the following. You've got your reference that goes into your adder. Okay, and that obviously will give out your error. We're going to multiply that by KD being a constant for the derivative control, just as Ki is a constant for integration control, and just as Kp is a constant for the proportional control. Okay, and that's going to be d dt, and that's going to go to an output u, and then that's going to come back and be fed into your adder or subtracted over there. Okay, so with your derivative control, basically it monitors the ramp rate and tries to prevent overshoot. So it looks at the ramp rate in terms of over time. Okay, so your general control books would then go and say, well, the formula for this is u of t is equal to kd d dt of e of t. Okay, so essentially if you had to put that into a means of, like we've done in a final sort of equation, you can say, well, u is equal to u plus kd multiplied by our current error minus our previous error. So essentially it looks at the difference between the errors in the previous iteration that we did. It compares it with the error that we've got in this iteration, multiplies it by KD, and then it adds it to the output u. Okay, so these are the basic overviews of the different controllers that you'll probably come across. And the way that I'm explaining it over here, yes, there's going to be a lot of critics going to say, wow, this is not exactly the truth, it's not 100% accurate in terms of the theory and stuff. Yes, I do understand it. I'm trying to bring it down into a simpler format for people to understand. There's a lot of this that is actually valid, but it allows you to then apply this to your actual mechatronics or robotic system. Okay, so keeping this in mind, sort of in the background, what I'm going to just do is there's a few other controllers based on that you might also come across. One is the PI controller. The proportional integral controller, and essentially what it does is it adds the different controllers together. Okay, so for this one you've got the equation u of t is equal to kp of e of t. That's the equation that we already know is for proportional controllers, and we add that to our ki integral from 0 to t of e of tau d tau, because that is your integration part of it. Okay, so again, if you had to implement this in terms of a mathematical way to do it in programming, u is equal to what u was plus kp. Okay, multiply that by our error. Okay, and then we've got plus kt, ki, and that's multiplied by the sum of from I is equal to 0 to I is equal to current of the error I. Okay, then you also get a PD controller, so that's proportional derivative controller. Okay, so your PD controller has got the expression of u of t is equal to, or it's a proportional part of it, so that's kp times e of t minus, so the derivative is subtracted, kd, which is our constant for our derivative controller, dt of the error of t. Okay, again, putting this into some form of code that might be relevant, u is equal to u plus kp multiplied by error, okay, plus kd, and we're going to say that is multiply that by our current error minus our previous error. Okay, and then finally you would come across what's known as the PID controller. So that's looking at all three controllers, that's proportional, integral and derivative controllers. Okay, so your PID controller has got the expression of u of t is equal to kp e of t plus ki integral from 0 to t of the error e of tau d tau minus kd d dt of e of t. Okay, so looking at this now, if we had to put that into an expression that we would probably use in coding, u is equal to, remember u is our output, u is equal to whatever the output was, plus kp multiplied by our error, plus ki multiplied by the sum of our errors I, minus kd of our error current minus our error previous. Okay, so those are the expressions that you would commonly come across and use. Now again, a final sort of line in these pieces is what essentially we're going to be looking at. And so U is actually what we can do is, because our output often to some motor is PWM, we can say our new PWM value is equal to what the previous PWM value is, in other words U, plus this expression afterwards. And our error could be in terms, you might have to relate your U value over here in terms of PWMs correlating with speed, but it all depends. It's very dependent in terms of what the actual system is. Now keep in mind that like I mentioned to you, your input and your output in terms of motors are not always linear. There's what's known as hysteresis curves. There's, in other words, with the magnetic fields involved, it will actually cause an increase or increase of your input is needed until the output can actually start. So it's not a linear system of S21 S21. Once that magnetic field is overcome and you get motion in the motors and that momentum is overcome, then you might get some linear aspect to it, but then later on it might go off and not be linear again. So that's the reason why these controllers are quite useful, to be able to monitor that and see how things are going. Okay, so now that we've looked at the different controllers and essentially how we're going to implement with these final lines in our code, at least that's what we're going to try and do. Because essentially, if you look at this, what we're going to be doing in our code, which we'll look at in a video or two later, is that every 100 milliseconds, we're going to let a timer interrupt, and we're going to check how many counts we've got in terms of our optical encoder. So we're going to count our optical encoder value. And if we know we've got, let's say, 250 counts within that that we've read within that 100 milliseconds, we can correlate those 250 counts in terms of what is the actual speed of the motor. So we know that these 250 counts might be in terms of an encoder that's got, let's say, 500 pulses per revolution. So that will give us then how many times we've got this, or how many degrees we've even achieved in terms of this. So we could multiply it by 360 to get an angle, or we could get an angular speed to multiply it in terms of how many times it's actually gone around. This value over here could be maybe 1,250. So we divide by 500 because we know that that is equal to 1 revolution, and then that will give us an indication of 2.5 revolutions that we've obtained or achieved. And then with that, we can then sort of see, okay, well, what is the value we actually wanted? We can then use these equations that we've done for our PID controllers, and then we can, from there, the system will correct it and it will give out the right output as we desire it to be. Okay, so now that we've looked at this, we need to look at, we've essentially looked at our variables of Kp, Ki, and Kd. But how do we tune these values? What values do we give these constants Kp, Ki, and Kd? Now the thing is because our systems is not always linear, it's not always the same. There might be friction involved, there might be some resistance involved. It's difficult to go and say, well, every system is going to be the same, and therefore I'm going to use the same values for these. So what I'm going to be telling you at the moment is a bit of the process that you go about tuning it. It's a little bit of a rule of thumb type of scenario as well, but it doesn't always apply. Okay, so to give you an example, Okay, let's look at the PID controller, or the P controller. So our P control. And essentially what's going to happen is you're going to have this specific graph that you want to obtain. So it might be something like that. You're going to be putting some step into it. Okay, so there might be a step that you are going into this specific output. Okay, so with your PID controller, what might happen is that it might go, and if your KP value is too small, it might not get to the set point. So that's a step we want to obtain, that we put in, and we want to try and reach this goal of that. That's the value that we want to get. So if your KP value is too small, you might find it going up, and then it's going to just even out over there. There might be maybe a little bit of overshoot maybe happening, but nonetheless it will even out over here. It won't get to that set point over there. Okay, what happens if we've got now a KP value that is too large? Okay, so now you want this desired position over there as indicated. So now what's going to happen is, if your KP value is too large, it's going to come up, it's going to overshoot, and it's going to start oscillating. And when I say oscillating, it's going to go higher and higher, and it's going to not converge to the set point we want. Okay, so obviously you don't want KP to be too high. Okay, so journeying with your KP values, what you would find happening is if I can call it the ideal value that you want to obtain, will essentially appear something of the fashion of you come in, you get a step response, or the set point you want to go, it will go up, and there might be some oscillation happening over there, and then eventually it will converge to the point over, to the set point that you want over there. The problem is that you want to minimize these oscillations as well. Okay, so that is what's going to happen. Essentially, the bigger your KP value is, the quicker you're going to be able to get to the set point. If it's too low, it might sometimes, if it's higher than the too low value where it doesn't even get to your set point, you might find that it would actually increase, and then it will take for a long time before it actually gets to the set point, and then it will oscillate stuff. So you want to have your KP value to be as high as possible, so you can reach that set point. And as I mentioned to you with proportional control, it is where the output is proportional to the error. So you want to try and reach that set point as quickly as possible. And that's what you do with your P controller. Okay, so how do you go about tuning for your proportional controllers? Well, essentially, it is a trial and error type of scenario. And so you will go and you've got your monitor, your output that you want, and you'll give it a certain set point that you want to achieve. Okay, so you will keep on increasing your proportional value. Okay, and you will monitor when it is getting to the point, or what the value of the proportional control is before it starts oscillating and go out of control. Okay, so what we will do is let's say we set KP equals to, and I'm going to just use the number over here, let's say 500. Okay, so at 500 you see it goes up, and there's some oscillation happening over there, but it converges eventually and goes to the set point. Then you say, okay, well, what about KP equals to 550? So you do the experiment again, and you'll realize that what's happening is it will come and it will start going up, and then it will start oscillating and going out of control and get bigger and bigger, this wave. Okay, so what you'll do is you'll say, okay, well, in that case I'm going to take just 500. That's just below the point where it goes out of control and starts oscillating. Okay, so then you can say, okay, well, if KP is equal to 500, what I'm going to do is I'm going to divide it by 2. That's going to equal to 250. Okay, so with 250, if you had to do that same test, what you might see happening is that you'll have some step that you initiating over there. So it will come, you get to that point where the step is initiated, it might start toggling a bit, and then it will converge down to that amount. As a matter of fact, that's actually incorrect. What's going to probably more happen is you're going to find that it will, because we've halved that would be if you took it at the value of 500. So now that we've halved it, you'll probably find that it will do something of this following nature. It will go up, it will probably it will overshoot, might overshoot only a little, and then eventually it will go to the set point over there. Okay, so then we will say, okay, now we've got our KP value, and we'll leave it at that. Okay, now once we've done that, we will then start looking at the integral controller. Okay, so what's going to happen is if your KP value is too low, you could have the scenario where it is not going to reach a set point. So as I showed you an example in the previous one, if it's, and again this is where you're going to have to do your tests and stuff, if you set it to 250, so okay, so we've got now KP, we've set that to 250, you might find what's going to happen is it's going to come over here at that point, it's going to increase, it's going to oscillate over there, and then it's going to even out. It's not going to get to the set point that we want. Okay, and that could be because our KP value is too small. Okay, so therefore with the integral, it essentially is going to move that up towards the set point. Okay, if this Ki value is too low, then it's going to cause it, we're not going to reach a set point over there. If it is that it's too high, it's going to cause it to oscillate. Okay, so what we'll do is we'll start off with a Ki value of, let's say, 5 for example, and you'll start increasing it slowly and slowly until you see that eventually what your desired output is where you get up to the point where you ramp it and it goes up to the set point, oscillates maybe a little bit over there, and then it's equal to the set point. If you find that it should come down a little bit and it's just below the set point, increase that value of the Ki until you get it exactly over there. Don't worry about the overshooting happening over here, we will get to that later. But essentially for now, you want to make sure that this final output over here is equal to the set point value that you've got. And test it for different values for your set point that you want to do. Okay, so that is for our tuning for the integral part of things. Okay, now we want to look at the derivative. Okay, and the tuning of that. Right, so what the derivative is going to do is over here where you've got this little bit of overshoot happening, it's going to try and accommodate that, and that's why the derivative term is subtractive. It's going to take away and try and sort of see what rate are we going over time over there and decrease it so that you don't get that overshoot happening. Okay, so again, you might say, oh, you know what, I'm going to start off with a value for our derivative tuning. We're going to use the same example over there. Okay, so we've got, let's say, Kp is equal to 50. You might find that over here, when we did this integration tuning, you might have found that Ki was best around about equal to, let's say 20, let's say maybe 20 or so. Okay, so now we've got Kp equal to 250, Ki is equal to 20. Okay, so now to eliminate that error, when we've got a Kd value, we might say, okay, we're going to have a Kd value equal to 5. And what's going to happen is that it will come, again, it will get there to the point where the step response is, it will start increasing, and it will eventually make that overshoot not happen. It might be that it overshoots a little bit, so therefore you would increase your Kd value. If you find that it goes over, you might find it does that type of shape, which might be considered acceptable. You might find that it actually, if your Kd value is too large, then or getting a bit too large, that it might even do that, which might be a bit more of a time period it's going to take until it gets to that desired set point, but you could have that type of shape happening. So you generally want to have a very small overshoot happening over here. When I say small, hardly even visible to the eye, and then smoothing out over there. Okay, so like I mentioned to you before, the ramp rate is to look at the derivative term is to look at the ramp rate and to prevent the overshoot. Okay, if your Kd value is too small, it will be as if you don't have, and it will be like your PI controller. It will still have that little bit of overshoot happening. Okay, if it is too large, it's going to then start becoming unstable, and there will be some distortion in your signal as well. Okay, so you want to try and figure out what is the right value for that. Now again, a rule of thumb, and like I say, this is not always the case. It depends on the system that you're going to be using. The steps I've just shown you in terms of the tuning for your PI and D controllers is essentially what you would do. But if you have a look at different PID controllers and what their parameters are, this rule of thumb that might be of value to consider. Once you get your Kp value, it might be equal to, let's say, X. Rule of thumb is that your Ki value would be roughly equal to X over 10. I've seen that happen, that it's roughly that amount. As a matter of fact, you could even try and simulate these inputs, and like we've looked over here, and you'll find that with the Kp of 250 over there, your Ki value is roughly equal to maybe 20, well, like I say, it's divided by 10, so it would be 25. You might find it evens out about 20, might even out around about 30. You need to, again, it depends from system to system, but a starting off point would be a good point. Say, well, maybe divide the value of Kp by 10, and that would be giving you a good Ki value. Okay, sometimes you'll find that with a certain proportional controller, like I mentioned to you, you've got your PD controllers. Maybe you don't even need the integration one. Maybe the Kp value is sufficient. There isn't much of an overshoot for that specific system. It gets your set point, but you want to eliminate that overshoot. And therefore you use your PD controllers. So you would not have the integration term to worry about, and therefore you can able to get a good graph by eliminating the integration term. Okay, now something that's quite interesting that we've experienced before, and that is with unmanned aerial vehicle, or UAV, or a drone, whatever you want to sort of refer to it. And generally you've got these Pixhawk programmable controllers that you can program for these unmanned aerial vehicles. And there's other boards as well available, like the Krios board, and there's other brands that are also available and stuff. Yet we found that we had 3 different modes with this specific UAV. We had one that's our manual mode, we had one that was our automatic mode. So that was looking at an autonomous flight type of thing. And then we had our GPS control flights. And we thought, oh wow, okay, that's going to be easy. Once we're in the manual mode and we know what our KP value is, we know what our KI value is, and we know what our KD value is, we've then essentially tuned in these parameters and we're able to use it for any of these other flight modes. The problem came in whenever we use these KP, KI and KD values for autonomous or GPS mode, it wouldn't actually work. Okay, so again, even between different modes, you're going to need different constant values for your proportional, integral and derivative terms. Okay, so with what we've now looked at, we're going to be essentially implementing a very similar type of system in programming. I'll show you how to write the code for that when we get to that part of the videos. And then it will be essentially where you will see I've actually got as variables the KP, KI and KD values. I don't program them as hard code in the equation itself, but as variables, because then it's easy just to change these variables and to increase them and decrease them. And then from that, you're able to either monitor the outputs, monitor maybe the speed of the motors, and then see how it performs. And then you can even plot these graphs if you want to. And then you can adjust these values and tune them to the desired values that you want.